disrupted into 20 some odd pieces, go crashing into Jupiter. One by one, these pieces crashed into Jupiter. Wham, 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 releasing tens to hundreds of thousands of times more energy than the most powerful nuclear weapons known on Earth. We'll move on to other planetary systems. How did they form? Well, they form from giant clouds of gas and dust, gravitationally contracting to form central glowing objects surrounded by disks of debris, gas and dust that can in principle coalesce to form planets. And we see these disks of debris around some young stars. And there's even a lot of evidence now for planets, real live planets orbiting other stars. About 200 planets outside our solar system are now known. It's incredible, and they were found just in the last decade. This, of course, rekindles our interest in the question, is anybody out there? One of the greatest mysteries of all time. Well, you might say there's lots of evidence for other creatures being out there. Look, here's a publication that says that an alien endorsed the Texas governor, and ecstatic aides said that he's a shoo-in as a result of this. Well, of course, don't believe everything you read in newspapers and tabloids especially. It's a legitimate question. Did life, complex DNA or something like it, form elsewhere? And did it evolve up to a state of intelligence comparable to or even exceeding ours, where it can contemplate the vastness of the universe and its contents? We don't know, but we're trying to find out. And we're trying to find signals from possible extraterrestrials intentionally or unintentionally communicating, sending electromagnetic waves through space. You can find them, you can detect them in principle using large radio telescopes. And we'll even explore the possibility that one could traverse the vastness of space in a spacecraft and visit other stars, other planets. It turns out to be very hard to do. The stars and their lives will be our next topic. We will consider their distance, size, power. It turns out stars come in a variety of sizes, like Betelgeuse, the upper left shoulder of Orion. The constellation Orion is a giant star which would go nearly out to the orbit of Jupiter if Jupiter were orbiting that star. It's a supergiant. Stars orbiting one another allow us to determine their masses. By studying the mechanics of their motions, you can figure out their masses. And looking at clusters of stars, you can figure out ages of stars. Here's a cluster that happens to be fairly young. It's an open cluster. Here's a much more concentrated globular cluster, which is 12 to 13 billion years old, one of the oldest objects known in the universe. And we will explore how it is that stars produce the energy that we see. They do it through nuclear reactions deep in their core, the fusion of hydrogen into helium, and later in their lives, the fusion of helium to other heavier elements. Now, some stars aren't quite massive enough to fuse hydrogen. We call them brown dwarfs. And here's a little one in orbit around a normal star. And this brown dwarf is barely glowing. It's very difficult to detect. But our sun, of course, is bright. It's got a lot of nuclear reactions going on inside. Will it last forever? No, it won't. Later in its life, it'll blow out its outer atmosphere of gas in gentle eruptions, or cosmic burps, I like to call them, forming a glowing nebula with a dying central star in the middle. That'll be a beautiful sight. And in the end, the sun will turn into a highly compressed remnant, a white dwarf, comparable to the Earth in size, but having a density, a mass per unit volume so high that a teaspoonful of material would weigh several tons. We will then explore explosions of stars and black holes. Some stars explode at the end of their lives, releasing material that gets ejected into the cosmos. And this material is chemically enriched in heavy elements because the explosion produced those elements and also liberated the heavy elements that had been previously produced by nuclear reactions in the normal course of the evolution of the star. The remnants of such explosions, like the Crab Nebula, go flying out, and from that enriched set of gases, new stars and planets and ultimately life can form. Well, at the center of an explosion, you sometimes have a compact remnant called a neutron star, a star having roughly 1.5 times the mass of our sun, but compressed into a volume whose radius is only about the size of a city, maybe 6-mile radius or something like that. Incredibly dense material, like a gigantic atomic nucleus. Such an object bends or warps space and time around it. And if the object is sufficiently compressed, the warping of space and time is so extreme that nothing, not even light, can get out, and that then is called a black hole. And here's my prize-winning photograph of a black hole. Black holes can be detected by their gravitational influence on companion stars, which are sometimes bound to them. You can actually see material that the black hole is stealing from the other star, and that betrays the presence of the black hole. And theoretically, at least, some black holes might provide passages or wormholes to other universes. Can you really go through one of these wormholes? It turns out you can't, probably, but the mathematics suggests that in an idealized case, you might be able to. Black holes form, in some cases, we think, by the collapse of very massive stars, which produce momentarily a brilliant burst of radiation, often at high energies, gamma rays. And some of these so-called gamma ray bursts might also be produced by the merging of two neutron stars or of a neutron star and a black hole. Bam, there it goes, increasing the mass of the black hole and forming two jets of material that are oppositely directed. This coalescence of neutron stars and black holes should lead to gravitational waves, ripples in the very fabric of space-time that go out from the coalescing neutron star, betraying its presence if we someday detect or build detectors that are sensitive enough to actually find this radiation predicted by Einstein's general theory of relativity. We'll then move on to galaxies, first considering our own galaxy and the sun's position in it. Let's take a journey through our Milky Way galaxy, exploring its contents and its structure. We head toward the familiar constellation of Orion. You can see the stars of the belt, and below them is the sword of Orion. Inside that sword is a giant cloud of gas and dust, forming stars right now as we speak. It's a gigantic stellar nursery about 1,500 light-years away. We move past other such nurseries, the Horsehead Nebula, where again stars are being formed as we speak. And there are nebulae throughout our galaxy, sites of active star formation. This one here, the Rosette Nebula, formed some very massive luminous stars which subsequently blew a bubble around them, a hole in the nebula. Moving on, out farther from the sun, we go past the Crab Nebula, the remnant of a colossal explosion that was seen by Asian astronomers about 1,000 years ago. There are chemically enriched gases in those clouds, gases which will later form new stars, planets, and perhaps life itself. Moving out of the plane of our Milky Way galaxy, we begin to see its true grandeur. We can't get such a view from within. But from above, we see the beautiful spiral structure and the companion galaxies, the large and small Magellanic Clouds. We live in a cluster called the Local Group, consisting of a few dozen galaxies. The major companions in our Local Group are the Andromeda Galaxy, seen at left, and another one, M33, through which our journey takes us. There's a giant nebula, a stellar nursery, in M33, and we whisked right through it. Now we will go and explore other galaxies, ones that are outside our Local Group. You can see very distant ones back there, but here we go right past M81 and M82, just 11 million light-years away. And here's another one, M101, a beautiful spiral galaxy, and then the Whirlpool Galaxy, M51. Looking at this vastness of space, we see all these fuzzy little blobs, other galaxies like our Milky Way, like the Andromeda Galaxy. There are thousands of them. We first go through a loose group called the Ursa Major cluster, and then we turn and head toward a massive, giant cluster of galaxies known as the Virgo cluster. It's about 60 million light-years away, and it contains over 1,000 galaxies. The central galaxy, M87, is enormous and has cannibalized small galaxies in its vicinity, and we think it even has a gigantic black hole at its center. Turning finally to cosmology, the universe as a whole, we will first consider cosmic expansion. You look at all the galaxies and they appear to be moving away from one another. We think the whole grid of space, the whole coordinate system is growing, and the galaxies themselves are remaining about the same size, but their distances from one another are growing. We can use this relationship, speed of a galaxy versus its distance, to determine the distance of a galaxy by measuring its speed of recession away from us. And knowing the distances of galaxies, we can then figure out how far back in time we're looking. If we examine extremely distant galaxies, billions of light years away, we see that they look different from our Milky Way and other nearby galaxies. Galaxies evolve with time, and by looking at progressively more distant ones, you can monitor that evolution. Looking in the hearts of some galaxies, we will find evidence for supermassive black holes, millions or even billions of times as massive as our Sun, devouring material in their immediate vicinity. And the most extreme example of this are the quasars, extremely distant luminous denizens of the distant past, where a black hole is devouring material at a prodigious rate. We will then consider the structure and evolution of the universe as a whole. What is its overall shape? What is its size? When did the universe begin, and how will the universe end? Is our universe like an infinite flat sheet of paper, but in 3 dimensions? Or does it wrap around itself, like the surface of a sphere? Or does it curve in a negative way, like the surface of a horse's saddle? There are ways we can tell by testing various geometric properties of space. And we can also look at when the universe might have started by extrapolating the observed expansion of the universe back in time to the Big Bang, the beginning. When did the universe begin? Extrapolating forward in time, how will it end? Will it keep on expanding forever? Or will it recollapse when gravity takes over and causes all these galaxies to collapse in on each other to a big crunch, the inverse of the Big Bang? Well, we now think that that's not going to happen. We think that based on today's information, the universe will either expand forever or for a very long time. And that's because observations of distant exploding stars, supernovae, actually tell us that the universe right now is expanding more quickly than it was 4 or 5 billion years ago. The expansion of the universe is not slowing down with time, it's speeding up, as though the universe is filled with some sort of a cosmic anti-gravity. Imagine Einstein's reaction if he were alive right now to hear this conclusion. The reaction might have been something like this. Observations of the afterglow of the Big Bang, the faint hiss at radio wavelengths that fills the universe, confirms these ideas that indeed the universe seems to be filled with some sort of a dark energy causing a cosmic repulsion. That dark energy dominates the total energy and mass of our universe. 3/4 of it is some sort of weird, repulsive stuff. Most of the remaining quarter is dark matter of an unknown type. We don't know what it is. What's the dark energy? Who knows? But it might be quantum fluctuations in space itself, or it might be related to theories that postulate the existence of other dimensions, spatial dimensions that are wrapped around on such small scales that you can't see them, kind of like the granularity of a sheet of sandpaper. Finally, we will consider the birth and origin of the cosmos and other frontiers. We will see how early in the history of the universe, the lightest elements and their isotopes were cooked up in the fiery bath of the Big Bang, primordial nucleosynthesis. And we will see how unified theories of the forces of nature may even explain how the universe began and how it grew to such a monstrously large size early in its history, like a balloon being inflated by a tremendous factor. Where did the universe come from before inflation? Well, we don't know, but it may have been a quantum fluctuation out of nothing, the ultimate free lunch. And indeed, there may even have been multiple cases of universes in a grander structure, the multiverse. I'll end in the last lecture on a philosophical note with some reflections on life in the cosmos and of our place in the grand scheme of things. It's amazing to me that we humans have the intellectual capacity to ask deep questions and to devise methods for learning how the universe works and how its contents evolve with time. Get ready for a fantastic voyage through the universe. we will explore just about all of the major topics in astronomy. I promise you a ride that you will never forget.